100,000 years ago, the northern half of the planet was buried beneath ice. Not snow, not winter, ice. A wall of frozen water more than a mile thick, grinding mountains flat, dragging forests south, erasing coastlines. Sea levels fell nearly 400 feet. Zoom into modern coastline. Water drains away. Land bridges appear. You could have walked from Siberia to Alaska, from England to France, across land that no longer exists. This was not an accident. Mammoths walking across tundra. Visual of mammoths walking across tundra continued. Zoom out to Earth in space, half the planet covered in white. For millions of years, the Earth has followed a rhythm. Cold, then warm, then cold again. Roughly every 100,000 years, the ice returns. When it comes, continents change shape. Oceans retreat. Ecosystems collapse and rebuild somewhere else. Most species do not survive unchanged. Ice advancing toward a glowing modern city skyline. Civilization does not exist during most of Earth's history. Warmth is the anomaly. Ice is the rule. Cold for 90,000 years. Warm for 10. Again and again and again. The ticking grows slightly louder. We are living inside one of those warm gaps. An interglacial, a temporary thaw. A pause between freezes. If the pattern holds, the ice always comes back. Long before satellites, before climate models, before anyone spoke of orbital cycles or deep time, a Swiss carpenter stood in a quiet alpine valley and noticed something that did not belong. The man's name was Jean-Pierre Perraudin, and what caught his attention was not a theory or an equation, but a stone, a massive granite boulder sitting in a valley made entirely of limestone, miles from any cliff it could have fallen from. It was out of place, impossible, and it wasn't alone. The valley walls were scarred with long parallel scratches carved deep into solid rock, as if something vast and heavy had once dragged itself across the land with relentless patience. The marks all pointed in the same direction, down from the mountains. Perraudin proposed something radical for his time, that these boulders had not fallen, and they had not been carried by a biblical flood, but that enormous rivers of ice had once filled these valleys, transporting stone the size of houses as they slowly advanced and retreated. He was not a professor. He was not a scientist, and so no one listened. It was only when he convinced a Swiss engineer named Ignaz Venetz to look more closely that the idea began to move beyond the valley, climbing slowly into the halls of scientific debate. Venetz measured the scratches. He mapped the boulders. He followed the evidence wherever it led. A young geologist named Louis Agassiz traveled into the Alps to disprove the claim. Convinced that the idea of a world buried in ice was exaggerated folklore, he left convinced of the opposite. Agassiz proposed that glaciers had once covered not just valleys, but entire continents, that Europe itself had been gripped by ice thick enough to reshape mountains and redirect rivers. The scientific world laughed, but the rocks did not laugh, and they did not lie. Across Europe and North America, the land bears scars from a force that moved tens of thousands of years ago. The rock is scraped. These are glacial striations, grooves carved into solid rock by ice sheets grinding forward like sandpaper over centuries. They all point in the same direction, down from the poles, driven by weight too immense to ignore. While rivers carve narrow V-shaped cuts, ice moves like a slow tide, shaving entire valleys into wide U-shaped corridors. As glaciers retreat, they abandon moraines, ridges of debris marking the exact edge of where the ice once stood. Look from space, and you'll see the Great Lakes, vast basins gouged into the crust as glaciers thousands of feet thick advanced and withdrew. Beneath the soil, repeating bands of gravel and clay record each advance and retreat, as though the planet itself were breathing in stone. No one watched continents freeze, but the evidence is everywhere. The Earth remembers. The ice may be gone, but the scars remain, proof buried in stone. But rock is only part of the story, because while continents bear scars, the ocean keeps something far more precise. A record. Beneath miles of water, layer after layer of microscopic sediment has settled quietly over millions of years, forming a vertical timeline stacked in mud and shell fragments, each band representing a different climate. Scientists call them sediment cores, but they are more than samples. They are archives. Inside these layers are the remains of tiny marine organisms called foraminifera, microscopic creatures that built their shells from the chemistry of the water. When they died, they sank, and they never moved again. Water molecules are not all identical. Some contain a lighter form, oxygen-16. Others contain a slightly heavier version, oxygen-18. During ice ages, vast quantities of the lighter oxygen-16 become locked away, leaving the oceans enriched in the heavier oxygen-18, and the foraminifera record that difference in their shells. When scientists measure those shells layer by layer, they uncover a pattern stretching back hundreds of thousands of years, a repeating pulse of cold and warmth, visible not in mythology, not in guesswork, but in atomic ratios preserved on the ocean floor. Cold, warm, cold again. And this pattern does not appear in just one place. It appears in the Atlantic, the Pacific, the Indian Ocean, independent records, same rhythm. Independent records, same rhythm. The ocean floor is not silent. It is a climate hard drive, storing every freeze, every thaw, every shift in planetary balance. And the rhythm never disappears. Cut. If the ocean floor stores the rhythm of ice ages in chemistry, the polar ice sheets preserve something even more intimate. They trap the air itself. In Antarctica and Greenland, scientists have drilled more than 2 miles into the ice, pulling up cylinders that formed one snowfall at a time, year after year, compressed under their own weight until each layer became a frozen page in Earth's atmospheric history. Inside those layers are microscopic air bubbles, and those bubbles are ancient. Some of them have not touched the open sky in 800,000 years. They contain the exact mixture of gases that existed when mammoths roamed frozen plains, and glaciers stretched across continents, not estimates, the actual air. When those bubbles are analyzed, they reveal a striking pattern. During glacial periods, atmospheric carbon dioxide falls to around 180 parts per million. During warmer interglacials, it rises to roughly 280, and this pattern repeats again and again. But the record also shows something else. Moments where temperatures rose sharply within decades, not centuries, reshaping ecosystems faster than species could easily adapt. The climate system is not only rhythmic, it is capable of sudden shifts. Temperature and carbon dioxide move together across the ages, rising and falling in synchrony, like two instruments playing variations of the same ancient composition. The ice doesn't just record temperature, it records atmosphere, and when the ice and the ocean tell the same story. When stone, sediment, and frozen air all repeat the same pattern, the rhythm becomes impossible to dismiss. The story of our planet is written in its most remote places, waiting for us to read the frozen pages of time. If ice ages follow a rhythm, and the oceans and glaciers confirm that rhythm across hundreds of thousands of years, then the question becomes unavoidable. What is keeping time? The answer may not be on Earth at all. In the early 20th century, a Serbian mathematician named Milankovitch began calculating how subtle variations in Earth's orbit might influence the amount of sunlight reaching the planet. He believed the sky itself might control the ice. The first variation is called eccentricity, a slow stretching and relaxing of Earth's orbit around the sun. shifting from nearly circular to slightly more elliptical over roughly 100,000 years. It is not dramatic, but it changes the distance between Earth and the Sun just enough to alter seasonal energy. The second is obliquity, the tilt of Earth's axis, which oscillates between about 22 and 24.5 degrees over approximately 41,000 years. When the tilt increases, summers become warmer and winters more extreme. When it decreases, seasons grow milder. The third is precession, a slow wobble in Earth's rotation, similar to the motion of a spinning top, completing a cycle roughly every 23 to 26,000 years. This wobble determines which hemisphere leans toward the Sun at different points in Earth's orbit. Milankovitch realized something crucial. Ice sheets do not grow simply because winters are cold. They grow when summers are too weak to melt the snow that fell the year before. If northern summers become slightly cooler, snow survives, and surviving snow becomes ice. When scientists compared these orbital cycles with the sediment and ice core records, something remarkable appeared. The timing matched. The ice ages seemed to follow the sky. But there was a problem. Of the three cycles, the one closest to 100,000 years, eccentricity is the weakest in terms of direct sunlight change. It barely alters total energy, reaching Earth. And yet, it dominates the Ice Age rhythm. The timing matches, but the math doesn't. If Milankovitch was right, then the Ice Ages should follow the strongest orbital signal. If Milankovitch was right, then the Ice Ages should follow the strongest orbital signal. But when scientists looked closer at the numbers, something didn't add up. But when scientists looked closer at the numbers, something didn't add up. Of the three cycles, obliquity, the tilt of Earth's axis, has the strongest direct effect on solar energy. Of the three cycles, obliquity, the tilt of Earth's axis, has the strongest direct effect on solar energy. At high latitudes, it changes northern summer sunlight far more than eccentricity ever could. It changes northern summer sunlight far more than eccentricity ever could. Logically, that 41,000-year cycle should dominate the Ice Ages. Logically, that 41,000-year cycle should dominate the Ice Ages. Beat, it doesn't. Beat, it doesn't. For the past million years, the climate record is ruled by the 100,000-year rhythm. For the past million years, the climate record is ruled by the 100,000-year rhythm. The weakest orbital variation, the smallest energy shift. The weakest orbital variation, the smallest energy shift, somehow controlling the largest climate swings on Earth. Somehow controlling the largest climate swings on Earth. The difference in total sunlight caused by eccentricity is less than 0.1%. The difference in total sunlight caused by eccentricity is less than 0.1%. And yet it coincides with ice sheets miles thick. Sea levels dropping 400 feet, entire continents reshaped, and yet it coincides with ice sheets miles thick. Sea levels dropping 400 feet, entire continents reshaped, and yet it coincides with ice sheets miles thick. Sea levels dropping 400 feet, entire continents reshaped, a whisper in space. Triggering an avalanche on Earth, a whisper in space. Triggering an avalanche on Earth. Scientists call this the 100,000-year problem. Why does the weakest cycle produce the strongest effect? Scientists call this the 100,000-year problem. Why does the weakest cycle produce the strongest effect? Why not 41,000 years? Why not 23? Why not 41,000 years? Why not 23? And here's where it gets stranger. Before about 1 million years ago, Ice Ages did follow the 41,000-year cycle. And here's where it gets stranger. Before about 1 million years ago, Ice ages did follow the 41,000-year cycle. Then something changed. The rhythm slowed. Then something changed. The rhythm slowed. The sky kept ticking, but the planet stopped listening. Cut. The sky kept ticking, but the planet stopped listening. Cut. For nearly 1,000,000 years, the ice obeyed a 41,000-year pulse. Advance, retreat, repeat. Predictable, stable in its instability. Beat. Then something changed. Around 1,000,000 years ago, during what scientists call the Mid-Pleistocene Transition, the rhythm slowed. The 41,000-year beat faded, and a new pattern took over. 100,000 years. The ice sheets grew larger. They lasted longer. They carved deeper valleys. They pressed the crust downward under their weight. Glacial periods stretched to nearly 90,000 years. Warm periods shrank. Sea levels fell farther. Deserts expanded wider. The climate swings became more violent. The system did not just change tempo, it changed scale. And here's the unsettling part. The orbital cycles did not change. The tilt still shifted every 41,000 years. The wobble still traced its path. The sky kept ticking, beat. But the planet responded differently. It was as if Earth rewrote its own rules, as if the climate system crossed a threshold, a tipping point in deep time. Early humans were already alive when this shift happened. They lived through a world that became colder, harsher, less forgiving. The ice grew larger than it ever had before. The rhythm changed, but no one knows exactly why. Why? Cut! So if orbital changes are weak, what turns a small cooling into a planetary freeze? Ice does. Fresh snow reflects about 80% of the sunlight that hits it. Forests absorb nearly 90%. Oceans absorb even more. One surface bounces heat away. The other traps it. If northern summers become just slightly weaker, some snow survives. That snow compresses, it becomes ice, and that ice reflects more sunlight. More reflection means less heat absorbed. Less heat means cooler summers. Cooler summers mean more surviving snow. Ice makes more ice. This is called albedo feedback, but the name doesn't matter. What matters is the loop. A tiny orbital nudge starts it. The surface of the planet amplifies it. As ice spreads south from Canada and Scandinavia, it changes the planet's reflectivity. Entire regions begin bouncing sunlight back into space. The climate system locks into cold. The orbit whispers. The ice answers. And once the loop starts, it feeds itself. But ice is not the only amplifier. There's another one. Invisible. The ice doesn't just record temperature. It records atmosphere. Every time the planet enters a glacial period, carbon dioxide drops to around 180 parts per million. Every time the ice retreats, it rises again to about 280. The two curves move almost perfectly together. Cold world, low carbon. Warm world, higher carbon, again and again. Carbon dioxide is a greenhouse gas. It allows sunlight in, but it slows the escape of heat. During ice ages, the oceans grow colder. Cold water holds more dissolved carbon. Like a cold soda holds more fizz. The ocean pulls CO2 out of the air and stores it in the deep. And it stores it in the deep. When the planet begins to warm, the ocean releases that stored carbon. CO2 rises. The greenhouse effect strengthens. Warming accelerates. The orbital cycles provide the spark. Ice amplifies the cooling. Carbon amplifies the shift. Small nudges become planetary swings. Carbon does not start the ice ages, but it makes them enormous. Ice reflects sunlight. Carbon traps heat. But neither works alone. There is something bigger moving beneath it all. The ocean is not a still body of water. It is layered. Warm water near the surface, cold water below. And at the deepest levels, water that has not seen the surface in 1,000 years. Scientists call it thermohaline circulation, a global conveyor belt driven by two forces, heat and salt. Near Greenland, surface water cools. As sea ice forms, salt is left behind. The water becomes denser, heavy, it sinks. And when it sinks, it pulls surface water down with it. That cold, salty water flows south along the ocean floor. It can take centuries to complete its journey, but as it moves, it stores heat, and it stores carbon. Eventually, deep water rises again near Antarctica. When it surfaces, it can release stored carbon dioxide back into the atmosphere. The ocean breathes, and here's where it gets dangerous. If too much fresh water enters the North Atlantic, from melting ice sheets, for example, the surface becomes less salty, less dense. It stops sinking. The conveyor belt weakens. Heat stops flowing north. Northern regions cool rapidly. The climate flips. Around 12,800 years ago, during an event known as the Younger Dryas, this may have happened. The world was warming. Then suddenly, it plunged back into cold. In decades, 11,700 years ago, the last ice age ended. The glaciers retreated, and forests returned to land, frozen for eons. This warm stretch is the Holocene, a brief intermission where every human civilization has existed in perfect climate stability. Agriculture flourished, rain became predictable, and cities rose. We built everything we know during this thin sliver of warmth. But today, carbon exceeds levels unseen for 800,000 years. The rhythm that held us is shifting. Orbital mechanics favor warmth. But human-driven carbon alters the balance, potentially delaying the next ice age for millennia. For the first time in history, a species has altered the planet's chemistry on a geological scale. Not over millions of years, but within centuries. For millions of years, the rhythm was untouchable. Now, we are part of it.